Hello everyone and welcome back to my channel. So today we are going to talk about trees as promised last week because we just covered the tree vocabulary. So we are going to do a specific example on a binary search tree, which I indicated last week as well, which is kind of the most important. So really long story short and a little recap. Also, before I start, thank you so much for all the subscribers. I'm very happy. I know last week's video, the quality wasn't so good. I need to get a new computer, so bear with me and be patient while I do this. It takes a long time for me to choose a computer because I'm a programmer, so I want the best. But I also don't want to spend the most amount of money on it, so let's just see. Anyway, so to look at the actual description now of this and go through a little summary before we start. So we said that lists, stacks, and queues are linear data structures, so they're in a line. So they're sequenced, which we know already, and we can insert into the sequence or we can remove from the sequence, and some are last in first out like stacks, and some you can like link lists together. A tree is non-linear, so it's two-dimensional data structure with special properties. So trees contain more than two links. So this section we're going to cover the binary trees whose nodes can contain two links. The root node is the first node in the tree, which we said last week, all the vocabulary that we learned. And just to summarize as well, that we have each link that in a node refers to a child. The left child is the first node in the left subtree, and the right child is the right subtree, is the right child. So children of specific nodes then have siblings, and roots without any or a node without any children is called a leaf, so they can fly away. So computer scientists normally draw trees root down, so you have like a little circle at the top, and then you've got little legs underneath, 1, 2, and more circles, and 1, 2, 1, 2, and so on. And the opposite of the way most trees grow by nature, because trees grow up, but we are looking from top down. So such a tree with no duplicate node values has a characteristic that the values in any left subtree are less than the value of the subtree's parent value. This is really important because this is how the premise of all this, when we calculate it, is how we're going to do it. So such a tree with no duplicate node values has the characteristic that the values in any left subtree are less than the value in that subtree's parent. So anything on the left subtree less than the parent. And the values in the right subtree are also the same. So now we are going to have a look at our three different classes. We will start like normal from the test, because when we start from the test, that is from the main entry point of the program, and then we'll go into it from there. So tree, and we're going to use again our boxed integer. So we're not using our primitive type, we are using, yes, reference type it is, integer, in order to use collections as well. So it's called tree, and then we have secure random. Also check out the secure random video, very fun fact with using random versus secure random, and a case in the United States that happened, which is kind of fun to talk about. That was in one of my very earlier videos from the beginner series. So then we write out the following values. We use our for again with a counter, because when you want to go from 1 to less than or equal to 10, so 1 to 10, incremental, and we're going to print out any number between 1 and 100. So we have system out here, and it prints it out, and we insert the value from the random into the node itself. So if I run the program, which we're going to have a look at the other two classes in very shortly, but we'll just see what the outcome looks like first. Bear with me. my computer is quite old computer right now. It's like 7 years old, so really need to get a new one. So we're inserting these values, 3, 34, 39, blah, 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 blah. This is now going to be our pre-order traversal, in-order traversal, and post-order traversal, which we'll come to in a second. But we basically, throughout this test program, we just call the methods in the tree class, which we'll go to next, I think. So pre-order traversal is just called, and it works its magic, in order traversal and also post order. And we've already inserted the values into the tree, so we're just ordering them in these methods. As you can see, they don't take any input, there's no parameters to it. So if there's no parameters to it, we've already inserted it here, so we don't need the parameters because they're already in the tree. So when we go to tree, which we will get to eventually, the storing into databases, because this only, all the data that we're running within these programs are only available when we run this program. But the next topic we're going to cover is concurrency, and then after that we'll do databases, so bear with me. We're going good. We're going good. So we have our tree class here. Again, we're going to use some very nice, neat things here. So we have our tree, then we have, it requires its type argument to implement the interface comparable. So with our interface comparable, this is going to allow us to compare to and sort and do all the fancy dancy things that we did before. If you're unsure, please check out that video as well, because it's pretty useful. So with every value inserted in the tree, we want to be able to compare it. That's where we're going to use the extends comparable. So we have instant variables here, tree node, which is private, and the class is private root. Then instance variables tree node is a reference to the tree's root, so that's why it's called root. So the constructor then initializes root to null. So this is our constructor. If you're unsure what a constructor is, please check out that video as well. So just quick summary, you have a class, you have every class comes with a default constructor. If you wish to change the constructor, think of constructor like constructing a building. I need a template. I need to know how many windows are in a building when I'm making it. I can then say in my constructor, I want 3 windows, and that would be a different constructor to I want 4 windows, and that would be a different constructor. That is what a constructor is. You're building a class. So here we have public tree. If you're unsure, please check out that video. Public tree, and then we initialize to null. Then we have insert node, which is the most important thing because we need to be able to put in values into our tree. So we already call this within the tree test class, and we insert the values from the secure random, which we already spoke about, and we insert those values from 0 to 99 it is actually, because insert 10 random integers from 0 to 99. And then we use our pre-order traversal, which is our public method, and that calls our private method. Now, if you're unsure about access modifiers, that's also something to be aware of, and we will continue in a second. So we have our insert node. If the root is null, then we want to insert, again, reading it from right to left. So we have our value that is going to be taken in here, 0 to 99, as we said, with our secure random. So 0 to 99 is now going to be in equal to the root. Then else we want to also insert our root insert as well. Okay, are you with me so far? Hope so. So it first determines whether the tree is empty. If so, then it goes to initialize it with the value being inserted in the tree and assigns the new node to the reference root, which we just said. So if it is null, insert Great. If the tree is not empty, then it uses the next, which is just plain insert. So then it just actually inserts, and we have our other methods down here as well. Let's go back up again. So in our tree node class, which we'll come to in a second, and we'll look at insert there, but we'll go down to our here. We should actually look at it first. So our tree node class has our insert. So when we have our root.insert, this is what it's doing. Because we need to use comparable as our interface, which is up here again, and we need to compare left and right. So the premise of that again being duplicate elimination. So binary search tree facilitates duplicate elimination, no duplicate values, which I said at the very beginning of this video. So tree node method insert compares the value to insert with the data value in the current node. So for instance, your node has 10. You want to insert the random number of 23. It compares 23 to 10. So that is now going to be the comparison to the root. So if the insert value is less than the current node's data, the program determines whether the left subtree is empty. So if the left is empty, then it allocates a new tree node, initializes it with the value being inserted, and assigns the new node to the reference left node. So you have your node, let's say it's 10, it's 23, so we're not going to insert it on the left. What do we do next? So otherwise it recursion as well, because we call itself, recursively calls insert from the left subtree to insert the value into the left subtree. If the insert value is greater than the current node, the program determines if the right subtree is empty. So everything on the right is going to be greater than the root. And the program determines whether the right subtree is empty and allocates a new tree node, initializes it with the value being inserted, and assigns a new node to reference right node. So when building a tree, the insertion operation recognizes attempts to insert a duplicate value, because a duplicate value follows the same go left or go right decisions on each comparison of the original, and then insertion operation eventually compares the duplicate with the node containing the same value. And at this point, the insertion operation can decide to discard the duplicate value. So in our tree implementation, if the insert value is already in the tree, it's simply ignored. So that's also a good thing. It's just ignored. So we're going to, every time here we have our insert. So if you have insert value compared to less than 0, and then we check if it's null. If it is, then insert it, else insert it on the left node, and the same with if it's greater than. So these two symbols are the most important part of this entire tree node. And now we're going to go back to tree again because we have our other three methods to talk about. So we have our pre-order traversal, in-order traversal, and our post-order traversal. And then they call tree what's called helper methods. So if you have if you have a public method that's being called and accessed by another class, you need a helper method. So respectively, you traverse the tree and print the node value. So helper methods, or accessor methods, you can also call them as well. As far as I remember, reference root is an implementation detail that a programmer should not have access to. So reference root, you shouldn't be able to access it. So by providing these helper methods, then enables client code to check and initiate all the traversals between and pass without the pass to the root node. Methods, pre-order traversal. Hopefully you're still with me. Pre-order traversal and in-order traversal and post-order traversal all pass the private. So we have pre-order traversal, which is public, and then we pass our helper methods, which are has the, I would maybe let's call it a suffix of helper. Let's not call it a suffix because that's not actually the definition, but you get my point. It's named helper as well. Same with post order and in order. So they're calling all of the helper methods that are private. So let's begin with in order traversal of the binary tree, which prints the node values in ascending order. So if we look here, here we go. So we check first if the node is null and then return in order helper, then node.left node, and then it checks, it sends it. It shows the data that's going to be passed into in order, and the same with printing it out, then the node.data, and the same with the right node. So traverse the left tree with the in order helper, process the value in the node, and then traverse the right tree with the call again to in order helper. So that's pretty much it for today. These three methods here, in order, post, and pre, if I'm looking at it like that, are actually three similar methods that are used, and just you can see the data is printed here, then the left, then the right, then the left, then the data, then the right, and then in the last one it's left, right, and then data. So just be aware that the process for pre-order is node, then pre-order again, and then pre-order again for the right subtree, so left then right, and then for post it's left, right, then the data. So the post order you can see when I press play again, and I'm going to keep speaking because we're just going to talk a little bit about binary tree search performance. So searching a binary tree for a value that matches a key value is fast. It's pretty efficient for tightly packed or balanced trees. In a tightly packed tree, each level contains about twice as many elements as the previous level. So a tightly packed binary search tree with n elements has log 2 to the base 2 n levels. Thus, at most, log to the base 2 n comparisons are required either to find a match or to determine that no match exists. There are other types of other tree algorithms as well. We've only presented the binary search tree ones. It's a two-dimensional tree, and it eliminates the duplicate, which we spoke about already. And then we also have the low order traversal of a binary tree, which there are other types that you can look at as well. So then to basically summarize, then we have looked at the main data structures. We've looked at linked lists, stacks, and all of the linear data structures that we spoke about, or the sequential ones. Now we've looked at binary search tree as well. Data structures are also important for the return call method as well. The different types of components that are when you're looking at the method calls as well. And next week we are going to look at, wait for it, concurrency. So we're going to look at concurrency next week, and then hopefully once we cover the concurrency topic, then we're going to go into databases. Thank you so much for watching. Happy Sunday. I hope you're enjoying the sunshine, getting some vitamin D, and I hope everyone stays healthy, wealthy, and wise. Thank you so much for watching. Bye.